Hi everyone. This video is the solution to example 1 on the topic of plastic beam analysis. The main idea of this topic is to find the plastic collapse load of a given structure. In this particular case, this example is a fixed beam with a load at 2 meters and the load is equal to W. And what we're trying to find is the value of W that would cause collapse of this beam. Another thing that we know is that the plastic resistance of the section is 80 kilonewton meter. So if you remember from the previous topic, we learned how to calculate something I called the plastic resistance, so MRD plastic. So the plastic resistance of a section, we learned a rectangle and we learned a T-section. So this topic follows the previous one, but we don't have to do this work because the question already tells us that the capacity of the section at the plastic range is 80 kilonewton meter. So if we know that, and we know that the section is in this given structure, we're going to learn how to calculate the collapse load of that. So how do you do this? The first step you need to do is to find the collapse mechanism that would cause the collapse of the structure. In this particular case, the collapse mechanism would be the following. It's a hinge underneath the loads and then two hinges, one at each support. And with this information, we can calculate the collapse load of the structure, assuming that the structure will collapse at these three locations. So how do we do that? The first thing we need to do is to draw the collapse mechanism. So in this particular case, it's a hinge on the left, hinge on the right, and then a hinge underneath the load. Once we have that, we're going to assume that a certain rotation theta will occur at one of the hinges. And when that happens, we can get that this shape, like this, will be the collapse shape of our structure. And remember that if we have a hinge here and here and here, right, if we have these three hinges, that means the rotation of our bars can be different. The same way that the rotation of the lower part of your leg and the upper part of your leg is different because you have your knee, right? If you have your top part of the leg like this, and then you have your knee, and then you have the bottom part of your leg, the rotation of the two is different, right? This is facing like this is facing like that, and the only way you're allowed to do this in your body is because you have a hinge, which is your knee, that allows for this relative rotation to exist, okay? So with these three hinges, this deformation is possible, so that's what we're going to try to calculate now. If the rotation is theta, another thing that we know is if this is 2 meters here, the displacement underneath the load will be equal to 2 theta. And again, this is where the load W is. Another thing that we know, if that's theta, this here is also theta. So I'm going to draw it here. And if the displacement here is 2 theta, and we're trying to find the angle on this right side, we know that that angle has to be a certain angle that when we multiply by 4 meters, we also get 2 theta. So in that particular case, the angle on this side is theta over 2, which also means this angle here is theta over 2. So with all this geometry taken care of, the next thing we need to do is to add the plastic moment every time we have a plastic hinge. So if we have a plastic hinge on the left, that means that the section needed to reach the plastic moment on the left side so that the hinge occurs. And that's valid on this hinge, but it's also valid here. So we have a plastic moment here, and another plastic moment, and also here, another plastic moment. Now, the final thing we need to do is something that we call the virtual work theorem, that we learned already in the context of the unit load method. But now, since no bar is deforming, the virtual work theorem is just an equilibrium of work from the loads and from the plastic hinges. So what we get in this particular case is we're going to add all the forces times all the displacements, and this has to be equal to all the plastic moments times all the rotations. So what we get in this particular case is the force times the displacement in this case is nothing more than W times 2 theta. So in this case, this is what we get, W times 2 theta. And this has to be equal to all the plastic moments times the rotation at that particular point. So if you look at the left side, we have let's mark it here, we have a plastic moment and a theta, so we're going to add it here, MPL times theta. But we also have another one here, right? And we have another one here times theta over 2, and we have another one here also times theta over 2. So if we add all of this up, we're going to get MPL theta, and then plus MPL times theta over 2, and one more MPL times theta over 2. Every time we do these equations, the value of theta is not important. That's why we can assume it to be just theta from the get-go. Because when we get to this equation, all the thetas will simplify. And we're going to land with the equation that is 2W equals, and now we have 1, 2, 3 MPL. So with this information, and knowing that MPL is equal to 80, that we got from the question in the beginning, that is equal to 80 kilonewton meter, we know that 2W has to be equal to 3 times 80, and therefore W is going to be equal to 120 kilonewton. Okay? And this is the collapse load of the structure based on this collapse mechanism. So this is the first example. We're going to solve a couple more, but the idea is this one. So yet again, we assume a certain collapse mechanism, we calculate what is the load necessary to cause it, and at the end, that becomes the collapse load that we're interested in obtaining. If you're wondering here, how do we know what is the correct collapse mechanism? The way you think about that is you have to think about what is the bending moment diagram in the elastic range. So the first bending moment diagram in this particular case should look somewhat like this. So we would have a maximum moment at the support, then we would have tension underneath the load, also maximum moment, and then also maximum at the support. So negative moments here and then positive moments in the middle. So if you look at this diagram, you will know that the maximum moments will be at the two supports and it will be in the middle. So in this particular case, the collapse mechanism is quite obvious because this is the only way it will make sense for the beam to collapse. In other examples, it might not be very obvious where the hinge needs to be. We're going to solve a couple more examples for you guys to see. But for now, this is a simple example just to introduce the topic. Thank you for watching and have a nice day.